Stanford. All right. Good afternoon, everybody. Thanks for tuning in. This week, we're very excited to have Albert Law, expert on quasi-normal modes. He's going to tell us about real-time observables in horizon thermodynamics. Please take it away, Albert.
Right. Yeah, thank you for the invitation and the introduction and the opportunity to speak. Well, I'm definitely not an expert on quasi-normal. Thinking about it though. So yeah, today I'm gonna talk about real-time observables in the horizon thermodynamics. So it's based on these couple of papers. So the story started, from this paper like 2 years ago with Klaus Parmentier, and then definitely review that, and there are some updated understandings that I'll report. Based on this recent paper with Manfred Groh and some work in progress in Andra Fassi. So before I actually talk about any real-time stuff, I will start by reminding everyone about the Euclidean method in quantum gravity. So in the Euclidean Path-Integral approach to quantum gravity, we'll look at an object of this form, which is a path-integral, Euclidean path-integral over some matrix and some matter field, periodic in Euclidean time. So operationally, what we do with this is we expand this around saddle points, and then we consider fluctuations around the saddle points. It's still an active area of research trying to understand even the definition of this object. What exactly do we sum over, things like that. But in any case, in the 70s, Gibbons and Hawking proposed that such an object should be interpreted as a thermo-canonical partition function like this. Okay, so essentially the intuition comes from, for example, QFT at finite temperature. If you have a trace e to minus beta h, you can represent that by path integral, right? So to just test this proposal to a zero order, we look for saddle points. For example, here the Euclidean black hole is a saddle point. If we have a Lorentzian black hole metric like this, and then we rotate it to imaginary time, and then we do this periodic identification. In terms of pictures, typically we deal with situations like this, where we have a horizon, you have some time like this, and then if you do this rotation and identification, then the horizon will be mapped to a point. Well, actually a codimension 2 surface, and then you have this contractible time cycle, and if you require the geometry to be smooth at right at this Euclidean origin, then that fixes the periodicity to be the Hawking temperature. So it's one way to sort of derive the Hawking temperature. Anyway, in any case, such a Euclidean geometry would arise as a saddle point in the path integral. And if you plug that into the path integral, then that actually yields the expected results in thermodynamics. So at least to the zero order, it works. Okay. And actually, since Gibbons Hawking, we've been using path integrals, and in some cases, we can see exact agreements with microscopic counting of black hole entropy, including corrections. However, I think it's safe to say that we never actually had a derivation from the Hamiltonian formalism, as opposed to quantum field theory, right? That's why I've been saying it's an interpretation rather than a derivation, right? which is not a problem when we can have a microscopic model, right? For example, string theory or ADS-CFT. But we don't always have a microscopic model. For example, in the context of de Sitter, we still don't have a very concrete model. Okay. And given the success of the Euclidean method, I think it's worthwhile to think a bit more about these tools. In terms of developing a Lorentzian picture, one approach that's popular these days is to actually we teach the Euclidean method and just directly work with algebra of observables in Lorentzian signature, right? That's one approach. But today, the approach I'm taking today is to actually look closely to Euclidean particle itself and try to see hints from there. And as I'll remind you later, at least at one loop, Euclidean black hole determinants actually they have some universal structures, which hints on some kind of Lorentzian interpretation. And on the other hand, in the Lorentzian nature, at this level of approximation, we're basically studying free fields on a fixed background. So hopefully I'll convince you that it is actually possible to understand both sides completely. And actually at the end, we'll say something about a more general formulation beyond one loop, right? Any questions so far? No? Okay. So here is just an overview of my talk. First of all, I'll review some of the results about Euclidean determinants, and I'll introduce this object called Quasinormal character. Okay, and then I'll dive into the Lorentzian nature and just analyze the wave equation, and then try to make a connection. Yeah, and then at the end, I'll say something about generalizing to interacting theories or even beyond that. Okay. So yeah, first part. Okay, so the leading quantum corrections to the path integral comes from quadratic fluctuations of matter fields and gravitons around the Euclidean black hole background. For example, for a massive scalar, the contribution at one loop would be expressed in terms of this functional determinant. From here to there, you basically expand your field in terms of eigenfunctions of the Laplacian, and then you can just do the Gaussian integrations. So by this functional determinant, we actually mean that it is a formal infinite product over the spectrum of the eigenvalues, the spectrum of the Laplacian, and here this D is a degeneracy. So this infinite product is actually UV divergent. Typically, you vectorize it by zeta function or heat kernel method. So yeah, okay. The basic question is what does this Euclidean determinant compute? Okay. So again, let's record the intuition from QFT at finite temperature. So there, I already said it before, a thermocanonical partition function has a representation in terms of path integrals. So here, just in terms of pictures, I just remind you how that goes. The point is basically that you think of this, you want to compute this trace in the field basis, right? So essentially, you look at an amplitude like this, and then this e to the minus beta h gives you Euclidean time evolution. The trace is implemented by identifying the initial and final field configurations, and then you integrate them over. Okay. So pictorially, yeah, well, it is computed by path integral, on a cylinder, basically. So because of this intuition, it seems reasonable to interpret the one-loop determinant as some kind of thermal partition function, right? So for some Hamiltonian, for the Hamiltonian in the Lorentzian nature, right, generating the time flow outside the horizon, and then the trace is the trace over the Fock space. Okay. However, if you think about it, okay, there are already two complaints. First of all, compared to the usual QFT at finite temperature, right here, the Euclidean time cycle is actually contractible. Okay, so which makes the derivation, not as clear. And then a second, actually more serious complaint is that if you actually think about, actually do the Lorentzian calculation, then you'll find that the spectrum of the Hamiltonian is actually continuous. So in this kind of situation, it's actually subtle to define a trace. Okay.
Can I ask
However,
a quick question?
yes.
Can you say a word about why the contractibility of the Euclidean time circle makes this is an issue?
It's just that how should I say? Well, it's not exactly a problem, but compared to this situation, it seems less clean.
Okay.
Right. It's just that, yeah. Oh, yeah. For example, in the black hole case, that will mean that this n will be actually a point, right? You have this sort of degenerate point. So this, you don't have this picture, right?
Okay.
In any case, so you can just say, oh, why cares, right? The Euclidean determinant, you can just compute some number. But it turns out there are some hints towards some Lorentzian picture. So I guess most notably is from this very nice formula derived by Dinev, Hano, and Sachdev back in 2009. They, based on some analyticity argument around the Euclidean origin, they derive a formula for the one-loop determinant in terms of quasi-normal modes. And quasi-normal modes are something that's defined in the Lorentzian signature. So at least, this formula sort of give a potential connection to the Lorentzian signature. Right.
Does this formula require that the Euclidean Laplacian has a discrete spectrum? The thing on the left-hand side?
Does it require? I'm not sure, but at the same time, I'm not sure if they implicitly assume that.
Well, I think they're usually working in ADS with this formula where the spectrum is actually discrete with
Yeah.
the normal boundary conditions. I'm just wondering about applying it to more general thermal geometries.
I'm not sure. I'm not sure. But yeah, but like you said, all the examples, this formula has been applied. They all have a discrete spectrum. You have in mind the cases of asymptotically flat.
Yeah, just like Kerr black hole, for instance.
Yeah. I'm not sure. I mean, yeah, let's think about it later.
Yeah.
Okay. In any case, so this is a very nice formula, and actually one way that I like to write this formula is in this form, right? So here, from the to get this formula, you essentially take a log of the previous formula and then use some string parameterization, and then you obtain a formula of this form. Okay, and then there is a clear structure. This factor here basically tells you is a boson, right? And then here I introduce this object that I called quasinormal mole character, which is basically a sum over quasinormal moles, right? And the terminology of character comes from the fact that in the case of a static patch in de Sitter space, it coincides with the Harshchandra character of the de Sitter group. Okay, for the element, yeah, for the DS boost element, right? And actually, the Lorentzian meaning of the one determinant will be more clear if we think about the Fourier transform of the Quasinormal character. So here, if you do this, then the one determinant can be written in this form, right? So here, this factor is a familiar boson sign factor. And looking at this, you can see that the log of the one determinant indeed takes the form of the free energy for a free scalar with, well, provided we can think of this guy as some kind of single particle density of states, right? And later, actually, I'll recall in what precise sense you can think of it as a spectral density, right? So before we move on, first of all, yeah, we have at least partially clarified the physical meaning for the one determinant through the Fourier transform of this object, chi. But here are just some questions. First of all, can we, is chi actually some kind of physical observable, right? Because, well, understanding the chi in terms of the Fourier transform seems a bit indirect. Well, it's a technical comment, you might not care, but I guess the second more serious concern is that it is not clear how to generalize to interacting theories, right? From what we discussed so far, right? It has a very specific structure that's for free theory. So yeah, it's not clear at this point. In any case, so in the following, I'll explain how to express the object chi in terms of Lorentzian propagators that will answer both questions, at least partially. Right. Any questions at this point?
Yeah, so in the previous slide,
Yeah.
is the analogy that you're drawing that we think of like chi of t as like the analog of the partition function, but for quasi-normal modes, and rho tilde is like the spectral density of quasi-normal modes, or
Okay, sorry.
so like yeah, pi is like a partition function for quasi-normal modes,
Yeah,
and like
roughly
rho tilde
speaking,
is
yes.
okay,
Yes.
yeah.
Yes. But yeah, later I'll actually explain that it is actually more appropriately be thought of as some kind of relative spectral density instead of a spectral density, because you have a continuous spectrum, and what makes sense to talk about in these situations is some relative spectral density. But I'll say more about that later. Any other questions?
Is it always a positive function?
I want to say no. It's definitely real, but I'm not sure. It's probably not probably not always positive.
I see.
Yeah, I think actually it's not always positive, if I remember correctly. Anyway, so yeah, now well, I'll start working in the Lorentzian literature entirely, and here just for concreteness, I'll focus on this specific case of free scalar on a de Sitter static patch. Even though later, I'll try to phrase everything in a way that does not depend on the fact that it's a de Sitter space, but just for concreteness, yeah, we have some model in mind. Yeah, we'll focus on a static patch, right? So here, this is the static patch metric. It covers sort of a 1/4 of the Penrose diagram of a de Sitter space. And this patch corresponds to a causal diamond for an observer sitting at the origin. And here, well, yeah, we have set the de Sitter length to 1, and there is a horizon at r equals 1 with this Hawking temperature 2 pi, right? So, well, to me, yeah, personally, a particularly nice way to think about to analyze a problem is to just first of all decompose the Klein-Gordon equation into an infinite set of 1D scattering problem on a half line, right? So here, I'm just doing well, expressing the field in spherical harmonics and decompose it, and then I also express the equation in this tortoise coordinate, so that the observer is still at x equals 0, but the horizon is pushed to x equals infinity. Anyway, so first of all, as a first step, yeah, we want to analyze normal modes for the wave equation, meaning we want to decompose the field in Fourier space, and then we define the normal mode to be the unique solution after normalization that is smooth at the observer. All right, so there is only one solution satisfied that. And for that normal mode, it is a mixture of plane waves of this form. So in terms of pictures, you can think of the solution as describing the following. So you have some plane waves coming out of the past horizon, and then bounce back off, bounce off some potential, and then go back to the future horizon. All right. From the 1D perspective, it is simple as this picture, right? So it is easy to show that for real omega, this ingoing and outgoing coefficients that compress conjugate of each other, and therefore the ratio is just a pure phase, right? And it turns out, right, actually this sort of asymptotic data, they basically contains all the non-trivial information about the spectrum. So one comment that I want to make now is about quasinormal modes. First of all, we can notice that the poles of this scattering phase, they are smooth at the observer, and they are purely outgoing at the horizon, right? So that's one notion on quasinormal modes. And at this point, I would love to also introduce the retarded Green function for the wave equation, which will be relevant later. So just to remind everyone, the retarded function associated with the Klein-Gordon equation is just, it's a two-point function that satisfies the Klein-Gordon equation with a delta function source, right? And here, the second condition is the so-called retarded condition, meaning that the retarded function is only non-zero for positive time, right? And actually, yeah, it is easy to show that this is equivalent to studying the retarder function for the reduced scattering problem, right? Oh, and also I've expressed things in Fourier space now. And here, just from standard formula of ODE, you can immediately write down a formula for the retarder function in Fourier space in this way. Here, the so-called Jones solution is a solution that's purely outgoing near the horizon. And then this so-called Jones function is just a Wronskian between the normalizable mode and the Jones function, right? And you can work it out the explicit form. You can, yeah, because the Wronskian is independent of X, you can just evaluate it at the horizon, for example. So here, yes.
Is the just solution just the quasi-normal mode solution, or is it?
No, here I'm just requiring purely outgoing, but not smoothness.
I see. Okay.
At the observer. Yeah. So omega here is still real. Okay. So here I want to make a comment about Quasinormals. First of all, as I said a couple of slides earlier, one notion of Quasinormals is corresponds to the scattering pose, meaning pose of the scattering phase, right? And explicitly in this example, well, and actually in all the examples you can compute things. You always see the scattering phase takes this factorized form, right? You have this, yeah, factorized form. I'm gonna explain what this is in the next slide. But yeah, here this is the important thing. You have these, two factors, and then the other notion of Quasinormals corresponds to the pose of the retarder function. That is the zeros of this Jones function. And here, clearly you see that this part, the pose of this guy, do correspond to the zeros of this Jones function, and therefore they correspond to pose of the retarder function. On the other hand, this mysterious factor, the pose of this guy, actually do not correspond to the zero of the Jones function. So what I'm trying to say is the two definitions of Quasinormals are actually not equivalent. There can be modes that are smooth at the origin and purely outgoing at the horizon that do not correspond to pose of the retarder function. Okay, is it clear? So here, yeah, it's just a comment about Quasinormals. And now, okay, in terms of this mysterious factor here, so it turns out that this part has a very simple meaning as follows. So near horizon, the space-time looks like a Wiener space. And in this region, the scattering problem reduces to this very simple form with a simple exponential potential. And one can show that the scattering phase for this problem is just this S ring in the previous slides. So let's go back to the question of spectral density. Yeah, like I said earlier, the spectrum is continuous in this case. So well, to sort of see that and it's subtly defined trace. And just to as an intermediate step, let's just cut off the space-time outside the horizon, and then just analyze the problem in this way. So if we put a cutoff and then put some boundary condition there, one can actually compute the spectral density in large R, right? And here by spectral density, I just means 1/4 the spacing, the energy levels, right? And you can actually compute this in large R, and you'll see that there is a leading term, and which blows up if you take the horizon limit, and then there is a subleading term, okay, that depends on the scattering phase, right? So the point here is that well, if you strictly send out goes to infinity, this rho blows up. But what's better defined here would be to compare the scattering problem with some kind of reference problem. Then differences in the spectral densities would be well defined in the R goes to infinity limit, right? And here, this is the key relation. This Klein-Friedel-Lloyd relation says that the relative spectral densities just depends on the scattering phase, right? So to make a connection back with the Quasinormal character, it turns out that the Fourier transform of the Quasinormal character that we saw earlier correspond to taking the near horizon Wiener scattering problem as a reference problem. So that is, this spectral density satisfies this relation. And if you remember, this guy takes a factorized form of some resonance part and the Wiener part. What I'm saying here is that this rho, and therefore the chi, and therefore the one determinant, captures only the resonances. Okay. Any questions at this point? If no, yeah, let's move on to make a connection between the Quasinormal character and the two-point function as I promised. So it turns out that the key object that will be related to the Quasinormal character will be the so-called spectral function or commutator function, which is basically the commutator of the fields sandwiched between the vacuum, right? And it is basically the difference between the retarded and advanced function, right? This function this spectral function is interesting because all the correlators can be written in terms of this through some spectral representation, right? So here, it takes some work, but one can actually derive a formula for the reduced spectral function in Fourier space. So basically, the idea is to, well, I shown you the retarded function in Fourier space earlier. You just take the difference of that, but you need to do some manipulation, and then at the end, you get this very nice formula. And here, to make a connection with the Quasinormal character, the key point is to think of the spectral function as the integration kernel associated with some integral operator. Okay. And then if you think of it this way, it is natural to consider the trace as an integral over the diagonal element. Okay, like this. However, the problem is that the integral diverges in the region x goes to infinity. Okay. So actually, in the same spirit as analyzing the spectral density, what we're gonna do is to cut off the integral at some large value r, and then study the large r asymptotics. Okay. And in fact, again, through some, after some work, one can actually compute the large R asymptotics. And you can see that, again, there is a leading term that diverges as R goes to infinity, and then there is a subleading term depending on the scattering phase. So by the same wisdom, we will consider a reference Wiener problem and then compute the same object, right? So yeah, the next step would be just taking the difference between these and then take R goes to infinity. And then finally one can obtain this very simple formula like this. Here, this tilde trace denotes the relative trace defined in this way. And then finally, if you take the inverse Fourier transform and then sum over all L, then you arrive at this very simple relation. So it just says that the Quasinormal character is basically the time derivative of the integrated spectral function. Right? Any questions at this point? Okay. If no, I want to say that, So these formulas, they're extremely simple, right? Which suggests
Albert,
that,
I mean, is this supposed to be a more general story? The Rendler subtraction is because specifically you have a horizon for this determinant, or is there some other subtraction that you're supposed to do if you're regulating a different problem?
Well, okay. Right. I mean, not sure if that's what you mean, but generally, I mean, there is no, at least right now, well, at least a priori, there's no principle that tells you that's something you need to subtract, right? You can subtract the quantity for a different reference problem. I guess the fact that we're doing the linear subtraction is, well, it's guided by the Euclidean answer.
Okay.
But a priori, you can subtract anything. Okay, you have something well defined. But okay, I don't have a lot more to say, but I think the factorization of the scattering phase into some resonance part and the Wiener part, that's actually something very universal for any horizon. You'll always have that Wiener factor.
Is that right? You have that just for like the Schwarzschild quasi-normal mode spectrum?
Well, okay, the case for Schwarzschild is a bit different because well, at least from this point of view, you have two asymptotic infinities, right? You have the horizon and also the really asymptotically flat region.
Yeah.
So I think there will be some Wiener factor associated to the near horizon region. Well, but probably not for the asymptotically flat region. I'll bet you'll see something Wiener there as well. But
Well,
I haven't
think
worked it
there's
out.
this family of highly damped quasi-normal modes in Schwarzschild, which basically are on the Matsubara frequencies, but they have like a small real part as well. So they're not exactly.
Maybe if you have two asymptotic regions, something will get corrected or something. I'm not sure.
Okay.
Yeah, but at least in this case or in like asymptotically ADS black holes, you will see an exact Wiener factor.
Really? Okay. All right.
Yeah. I mean, which is certainly true in examples. But I from what I've read, this
for BTZ, for instance, you would
yeah,
have.
in BTC, yeah, you see that factorization. You say yeah. Yeah, but okay. Again, I agree that okay. Purely from this perspective, it is not clear why you always want to subtract the Wiener part. Okay. Right. Anyway, so I was trying to say that yeah, these equations look very simple, suggesting there should be some simpler way of seeing these without actually computing both sides, right? Okay, and it turns out there is, and I'm going to describe that perspective. It's a more abstract perspective, but it is a useful perspective, and which I think will allow generalization. So first of all, here we want to view the reduced Klein-Gordon equation in this sort of abstract operator form, right? So here, in position basis, this Hamiltonian square just act as this Laplace type operator. Okay. So the normal mode solutions that we saw earlier, from this point of view, just correspond to single particle states, right, labeled by the energy, right? And here, in position basis, they are basically these wave functions. Here, this normalization, they are fixed by some normalization condition, right? So the idea here is that the wave function square, defines a local density of states like this. Okay, and this terminology comes from condensed matter literature. I just borrow them to this context. And we in this way, okay. Again, you can consider some the total spectral density. And again, by total, we mean an integral over x. The integral will diverge and you just subtract it off. But again, you subtract it by some Wiener part, you can define this total relative spectral density. Okay. So here, I'm just writing in this way. Okay. And again, one can show that the density, spectral density defined this way coincides with the Fourier transform of the character. And you can actually invert this, and it just shows that from this sort of single particle point of view, the character is basically some trace like this. Okay. So, and in this sort of operator language, the retarded and advanced function, they're basically the resolvents for the Hamiltonian squared, right? You can think of this retarded and advanced function as taking the inverse, right, of the wave operator. And here, the different IF prescriptions just would tell you whether the resolvent is analytic in the lower or upper half plane. And therefore, okay, in this language, the spectral function is basically a difference like this. And finally, using this representation of the delta function in this expression for spectral density, then yeah, it's almost trivial to show that you have this relation. Any questions so far? If no, here's a brief summary. So our story began with this DHS formula for the one-loop determinant, and from this very universal form, yeah, we introduced this object called a Quasinormal character, and I've reviewed that the chi is related to some relative spectral density for the free field. And in the context of static patch, I've explained the relation with Lorentzian correlators. And even though I use static patch as an example, our analysis actually applies to any black hole horizons. So if there any questions? If no, I want to say something that I'm mostly work in progress, and something I've been thinking about recently, about some generalization of this story. Yeah, and you can notice that the equations in this part are mostly schematic. In any case, so the first generalization, well, it's sort of obvious, right? We want to generalize the story to interacting QFTs on black hole background. So, and again, in an interacting QFT,
Sorry, Albert, maybe just before you go on. So when you said it applies to any black holes,
yeah,
is it obvious that you only have to do one subtraction for the Rindler side of the potential?
I'll bet,
from the other side as well.
Right, I'll bet for the asymptotically flat case, you also need to do another subtraction.
Sorry, what did you say? You have to do what?
I would think in the asymptotically flat case, you also need to do another subtraction for the asymptotically flat region.
So just like the density for a free space.
Yeah. I mean, essentially, it's a two-channel scattering, so you probably need to do both.
I see.
But I haven't worked anything out. But this, I would think that's how it will work. Yeah, but all other structures like scattering phase, blah blah blah. You can certainly define them in that context as well. Yeah. Right. So in terms of generalizing to interacting theories, first of all, a building block, for interacting QFT, again, are two-point functions, right? But here you consider two-point functions in the interacting vacuum, which would exist for this type of situations because you always have a conserved Hamiltonian, right? And one way to connect this with the free two-point functions is through these color element representations, right? So from this point of view, and also what we have considered so far, that will imply such a representation for the Quasinormal character as well. So schematically, you will see some representations like this. The left-hand side will now be defined as the time derivative of the integrated spectral function, right? I'm not, yeah. So I think it will be fun to think about, what this kind of representation can be used for, right? And then another aspects that I think will be interesting to think about is a horizon S matrix, right? So at least in the free case, right, we saw that you do have some kind of scattering matrix, right, for free fields, okay. And I think even for the interacting theories, the usual construction of an S matrix in flat space would apply. It would go through here, and it seems like they are very natural to consider, at least in the G Newton go to zero limit. In particular, okay, you can certainly construct as usual, these asymptotic creation and Gaussian operators as just in terms of a Klein-Gordon inner product of the free solution with the interacting field, and then you can construct in and out states using these, and then you can just define an S matrix as the overlap. Okay. So at least at this level you can certainly consider these, and recall in the free case, right? We express the one loop determinant or free energies in terms of the scattering phases. So the point of wanting to define something like an S matrix would be eventually to express thermodynamic quantities in terms of this S matrix, right? And in fact, there is a very old paper by Darshan, Marr, and Bernstein in the 69. They actually derive quite generally an expression of free energies, well, actually relative free energies in terms of some S matrix. Okay, so I think it will be very nice to think about this in the black hole context as well. And here, speaking of the interacting theory, it is natural to suspect that even for interacting theories, the Euclidean half integral is still a ratios of partition function like this. Yeah, just saying is something we might want to think about, right? And another generalization that we made some progress, but I haven't said anything about is the generalization to spinning fields, right? So far, I've only talked about scalars, but it turns out for spinning fields, in particular, right, Maxwell or gravitons, their one loop determinants actually have more structures in it. So yeah, quite generally, actually, the one loop determinant would be a ratio of this form, or product, depends on how you build it. Here, the bulk part is the same as before. You can really think of them as some free energy, well, some relative free energy, right, with the inner part divided out. And then you have some extra edge piece, okay? So a basic question is, yeah, what is the Lorentzian interpretation of this guy, right?
But does that path integral include the integral over the ghosts and gauge fixing stuff?
Yeah. What I'm saying is, yeah, after you do all that, you can put that formula into this form. Yeah, for a Maxwell, for example, yeah, this will be a ratio of determinants. Yeah, yeah. So more accurately, I just say it's a one loop path integral. Yeah. So recently, in this recent paper, we've studied the case of Maxwell, in this in the context of horizon, right? And in fact, what we found was that the z edge can be accounted for by some kind of edge modes living on the stretch horizon. So it's a long story, but the basic idea is that in the Lorentzian signature, you put some appropriate boundary conditions at the stretch horizon. You can incorporate these edge modes. They're related to some large K transformations. And yeah, upon quantization, you'll find that the Hilbert space factorized into some bulk part and edge parts. Okay, and the z edge can indeed be thought of as some trace over this edge part. Right? Again, it's a long story, but these edge modes, they are the horizon analog for soft modes in the asymptotically flat space. So I guess yeah, so I think it will be interesting to think about is there some kind of a soft theorem associated with that, and any kind of.
But why do you divide by the edge mode partition function if the Hilbert space is factorizing like that?
Well, actually, okay. Well, actually, I get well. From this point of view, it's actually multiplying instead of dividing. Yeah, I was so used to saying dividing because the form of the z edge is actually like, well, the edge partition function actually takes the form of a ghost complex scalar. So that's why I'm used to think of as dividing, but yeah, but I think from this perspective it's actually like multiplying. Okay, multiplying something ghost. Okay.
It has the wrong statistics, which is why.
Yeah. Yes. Right. Yeah, and finally, of course, we want to include gravity, right? And we want to understand. Well, yeah, if we turn on gravity, we need to consider, for example, back reaction of the matter fields on the geometry, or even include graviton interactions, right? So I think yeah, eventually I would love to understand how these will change the story. For completely non-perturbative, gravity, probably it might not make sense to well, to think that all these structures will remain intact. But for small G Newton, I will imagine it will be just some small corrections. For example, the 1D scattering problem will become some scattering, but with some kind of fluctuating potentials. Yeah, so I think yeah, it will be interesting to think about. Yeah, anyway, so yeah, I think this is what I want to say. Thank you for listening.
All right, thank you, Albert, for the very interesting talk. We have plenty of time for questions, so if anybody has any, just unmute and go ahead. I guess I'll start. I mean, has this been done for any black holes which are stationary rather than static? Like
No, unfortunately. But I think with this sort of updated understanding, I think we should be able to do those. Yeah.
Yeah, I'm interested just to do it for like rotating B2Z or something.
Yeah.
You still know the exactly. But can you tested these formulas, for instance, like in BTZ where you know the 2-point functions exactly and you know the spectra exactly and you can compare
For the
this.
BTC, I haven't done the 2-point function calculation.
Mhm.
Yeah, but in terms of the partition function scattering phase, yeah, we already did that. I mean, yeah, but the 2-point function, I mean, what I just described, the analysis I just described is just so general.
Yeah.
Yeah, it should just work, I think.
Well, I mean, did you assume anything about the singularity structure of the 2-point function? Because I think it can be a little bit more complicated when you have rotating, right?
By singularity structure, you mean like on,
Because you can have like null geodesics, which connect 2 points in very non-trivial ways. Like the bound null geodesics and
uh, maybe implicitly, but I guess whatever assumption, it will be related, if not equivalent to the assumption we put on sort of the space of functions we consider. Right here, I'm thinking of the retarded function as some, inverse of some wave operator, right? On some, space of functions.
I mean, your formula was some particular Green's function evaluated on the diagonal and then integrated
Yeah,
over the full space-time. Is that right?
yeah.
Generically, there's a singularity on the diagonal.
Well, no. Here is only diagonal in a spatial
But not
slice, right?
time.
Not in a space-time, right?
I see.
Yeah. So, yeah.
Okay. All right, do we have any other questions? All right, if not, then I'll thank Albert again, and I'll stop the recording.
Thank you.
We'll see everybody next week.